In today's notes, we're going to review the law of cosines and law of sines. And recall that the SOHCAHTOA definitions are only going to be useful if we have right triangles. So we need to have some more theorems to help us out in case we don't have right triangles. And the first one we're going to look at is law of cosines. We aren't going to prove this, we're just going to look at the theorem. And law of cosines first appeared in Euclid's Elements back in 300 BC, so it's kind of interesting that this has been around for a very, very long time. And if I have a generic triangle ABC, and notice how I've labeled all the opposite sides with the lowercase letters and the uppercase letters are for the angles, that if I have any triangle ABC, now this could be a right triangle, but it does by any means not need to be a right triangle, that law of cosines has three different forms, although you basically just need to remember one of them. And so remember, the idea is this. If I'm looking for, say, this little side, and if I know a nice little condition to remember is if you're given a side angle side or a side case, that the law of cosines is most helpful in solving our triangle. So if I am given this side, and this included angle, a side angle side, I can very nicely find the opposite side length by using law of cosines. So this opposite side squared will equal b squared plus c squared minus 2 times bc times the cosine of the included angle. Now notice how I can also write the law of cosines another way. If I were given, now in this case, this side A and this side C, and I knew the included angle B, I could find what this little opposite side is by saying b squared will equal a squared plus c squared minus 2 times the product of these two sides times the cosine of the included angle. And likewise, a third way to write it is if I know this side A and I know this side B and I know the included angle C, I can determine what this side opposite the angle is. C squared would equal a squared plus b squared minus 2 times the product of these two sides times the cosine of the included angle. Now do remember, when you use this formula, that order of operations is going to tell us that all of these numbers multiplied together are part of our term. You can't take the product of these three and subtract them away from the c squared. So we want to make sure that we know that this product, all of these act together as one part of our expression on that right side of the equation. So here's an example. I have a parallelogram, has a 70-degree angle, and it has sides that are of length 10 inches and 15 inches, and I want to find what is the length of its longer diagonal. Now, I want to review a couple things here before I actually show the picture. I know that I have a parallelogram. Parallelogram, by definition, is a quadrilateral that has two pair of parallel sides. So I have a parallel sides here, and I have parallel sides here. I'm going to make it look relatively close to a 70-degree angle. So this would be 70 degrees here. Now we also know, if I kind of extend this out, that this angle here would also be 70 degrees because these would be corresponding angles if these two lines are parallel. So if this is 70 degrees, we would also know that this angle here has to be the supplement of the 70. This has to be 110, which implies that these two angles will actually be supplementary angles as well. And again, because this angle is corresponding to this angle, and this angle is outside of the parallelogram naturally, but we can see that these two would have to be supplements. This angle over here is 70 degrees, and this side opposite here would also be 110 degrees. Now, where to put the 10 and 15 as far as the length of measures, again, I would obviously put this one as 15 just because I made it look as though it were longer than the other, but I could naturally have drawn it the opposite way and made this short and make this be an extended side. So there's my parallelogram. Now, the thing that a lot of people will come to conclusion to, and a wrong conclusion, is that when I draw these diagonals absolutely do not bisect these angles. If I draw that diagonal, this angle and this angle, you can obviously see that they are not congruent. Don't make that conclusion because it is not true. Likewise, if I draw this diagonal, it's not as obvious here, but this angle and this angle are not equal in measure. So there is no theorem that says that the diagonals of a parallelogram bisect the angle. Don't make up that theorem. That theorem is wrong. If this is a rhombus, then you will have that angle bisected, and that's only time where this angle will be bisected. So in parallelograms, almost always this diagonal does not bisect unless, again, you have all four sides being the same length, which makes it a rhombus. Okay, so I do have two different length diagonals. We can see that this length is definitely longer than this length. So when I want to determine the length of the longer diagonal, I have to be careful. This is the diagonal that I'm looking for, the one opposite the 110-degree angle. So I have my picture. And notice how law of cosines is going to be extremely helpful. We can't use SOHCAHTOA because we don't have a right triangle. We can produce some right triangles by dropping some perpendiculars down, but we won't know what those angle measures are. So the SOHCAHTOA definition is basically worthless for me. So I want to find what this side opposite of the 110-degree angle is, and I have a side angle side. And anytime I have a side angle side situation, I want to use law of cosines. So the side opposite is d squared, and that will equal this 10 inches squared plus this 15 inches squared minus 2 times 10 inches times 15 inches times the cosine of the included angle. So it's always a side angle side. I have one of the side squared plus side squared minus 2 times side times the cosine of the included angle. And then I do my calculations properly. Again, all of this will get multiplied together. Make sure my calculator's in degree mode. And I'd have 100 square inches plus 225 square inches minus the product of all these, which I can see is going to have square inches on it. This is what I get for d squared, square rooting it. I get 20.7 inches. Now again, look at your diagram and see if it seems like it makes sense. That length does make sense. I could likewise go through and draw this short diagonal and find out what the length of this short diagonal is as well, using side, angle, side. All right, so law of cosines is very useful if I have side angle side or side side side. So let's look at the side 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 situation. So I have a triangle that has lengths of 4 centimeters, 5 centimeters, and 6 centimeters. And I drew my picture relatively to scale, and I want to determine the angles for this. In fact, I put down find the smallest angle in the triangle. So I know that the smallest angle is going to be opposite the shortest side, so I will want to find the way I wrote it, angle A. So here's my side, angle, side. So 4 centimeters squared will equal 5 centimeters plus 6 centimeters, these are squared, minus 2 times the product of these two sides times the cosine of the included angle. Now again, I need to do my algebra correctly. I can combine these two together and add them. That's going to be 25 centimeters squared plus 36 centimeters squared. I can add those two together and then subtract that sum from both sides. I did that already and got negative 45 centimeters squared, because this is 16 centimeters squared. And then I had to multiply these guys together. So I had the negative 2 times the 30 centimeters times centimeters squared times the cosine of angle A. Divide both sides by negative 60 centimeters squared, and I have the cosine of my angle all ready to go. The cosine of my angle gives me a ratio. So I need to find the angle, so the inverse cosine of the ratio will equal my angle. Now I could likewise go through and determine the other sides, or the other angles as well, and have to use law of cosines again to determine one of these. Law of cosines is a very nice theorem because we will end up finding out that sometimes we can have a little issue with not knowing whether, with the sine function, whether we have an acute or an obtuse angle. But this ratio, if the angle happens to be something that is a second quadrant angle, this ratio will be negative. So you'll know whether you're going to get an obtuse angle here if this value becomes a negative ratio, you know when you inverse cosine, you'll end up getting an obtuse angle or a second quadrant angle. Okay, but we knew that this little angle A was the smallest angle in the triangle, so it had to be acute. All right, now we're going to look at another component, and not quite law of sines yet, but we're going to look at how do we determine the area of a triangle if we're given a side angle and a side. So if I'm given this scenario where I give you a triangle, and it's not a right triangle, I just have a regular old triangle, and I want to know if I give you what one side is and what another side is of the triangle, and I give you the included angle, how do I determine what the area of that triangle is? Now, we could do it the old-fashioned way where we could take and drop the perpendicular down, and we know that when we find the area of a triangle, we want to take the area to equal 1/2 the base times the height. And so if I knew how long this h was, I could take 1/2 of h times b, and boom, I could find my area. But we're going to have to do some calculation. So I know within my little picture that the sine of this angle is opposite, which is this little h, and I'm just looking at this little right triangle over here, that the sine of this angle is opposite over hypotenuse, which means that the height would equal this hypotenuse times the sine of that angle. And remember, we're being given the little side A, the angle theta, and the B. So now if I want to find the area of the triangle, I know the area of the triangle is 1/2 this base times the height, but I'm doing a substitution. I found out that the height was equal to A times the sine of theta. Now this is more typically the way that, just in alphabetical order, more typically the way the formula is written if we're trying to find the area of a triangle given a side angle side situation. So if I have this triangle, I take 1/2 the product of these two sides times the sine of the included angle. And look how nice that is. If I gave you this little scenario, here's just a little aside. If I told you that this is 3 centimeters long, and if I told you this is, say, 5.5 centimeters long, and I told you that the measure of this angle is 40 degrees, and I asked you to find the area of that triangle, it's very, very easy to find. 1/2 the product of the two sides times the sine of the included angle, and when I multiply this all out, I'll have the area of that triangle in square centimeters. Now, a very nice thing is we can use that formula for finding the area to actually prove law of sines. So law of sines is another formula that you used in FS, and let's look at where it comes from. So if I have my triangle ABC, as we did with law of cosines, and have the little sides opposite being the little a, little b, little c, and if I find the area of this triangle, I know that the area, if I utilize this side, and this angle, I would have 1/2 the product of these two sides times the sine of the included angle would be the area of this triangle. Well, this triangle could also be determined by using these two sides and this angle. So 1/2 the product of these two sides times the sine of the included angle would also be the area of triangle ABC. And thirdly, if I had these two sides and this angle, 1/2 the product of these two sides times the sine of that angle would also give me the same area of that same triangle. So all three of these area calculations would be equal. And if I divide each of these by 1/2 ABC, a whole bunch of things will cancel out, and I'll get my law of sines, which basically tells me there is a relationship between an angle and a side opposite in this triangle. So as this side gets longer, this angle will get larger, but it's not a 1-to-1 ratio. It's the sine of the angle over a side opposite is equal to the sine of an angle over its side opposite is equal to the sine of an angle to its side opposite. Now this theorem of law of sines excuse me, is useful under these conditions. We will get to this condition of the side angle in the next video, but for right now, If you have angle, side, angle, 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 side, very, very useful to use law of sines. You basically need to know an angle and a side opposite in some form. So let's look at this question. And then we'll be done with this page. So I have, let triangle, the measure of angle ABD, or excuse me, ACB, ACB was 26 degrees. We have the measure of angle ADB being 20 degrees, and we know that CD is 12 centimeters long. So we know this angle, and this side, and I've labeled them. And I want to find side BD, so this long length, and side AC. So I look at what I know, and there's some different things I can figure out by piecing together. I knew that this was 26 degrees. I knew this had to be 64 degrees because these two had to be complements in my right triangle. And if this angle was 20 degrees, and if this angle was given to me as a right angle again, then I would know that this angle here had to be, that whole angle had to be 70 degrees. So we could piece together and figure out that this is 6 degrees. We also knew these were supplementary, so this had to be 154 degrees here. And so basically I have all the three of these angles in this little triangle that I have over here. That would be triangle BCD. And I know one side, and I know all three angles. And the key thing is if you know a side angle pair, I know that 6 degrees is opposite 12 centimeters, and I know the other two angles, I can automatically use law of sines. So once you know a side angle pair, law of sines is your friend. So we set up the ratio. I'm going to put the sides on top rather than on the bottom since I'm looking for a side. I know that side BD is to its sine of the angle of its opposite, as side 12 centimeters is to the sine of the angle opposite it. Multiply both sides by sine of 154 degrees, and boom, I have BD. Now I actually stored this value in my calculator. Now I have a few different ways at this point to go through and determine what this side AC is, and I showed a couple different ways down here. One way is to go back and to look at this little triangle and determine what this side BC is with law of sines, which I did. BC is to the sine of the angle opposite, as 12 centimeters is to the sine of the angle opposite. Multiply both sides by sine of 20 degrees to get this. And then I would know how long this side is. And then I can end up using this little right triangle situation to determine what the length of my AC is. So we have that the cosine of angle 26 is equal to, and in the SOHCAHTOA definition, is equal to adjacent over hypotenuse. And I know that this hypotenuse in this little right triangle ABC is 39.3 centimeters. So I can find AC by doing that. I could have also worked with this big right triangle, and since I know what this hypotenuse is, I could use this angle 20 degrees and use the adjacent, cosine of 20 degrees is adjacent over hypotenuse, and I could have found what this whole length was and then subtracted 12 centimeters away to find AC. So there are a few different ways to do it, but there's one way. And that's it for this video.